This will hopefully be the first video in a series of many videos pertaining to the subject of differential equations. Now, differential equations is a very important subject, and some might say it's one of the most important subjects when it comes to the field of engineering or physics or mathematics, because it does describe many things in life using a more formal mathematical rigorous definition. For example, I have a bunch of pictures here on the screen, and to the unbeknownst eye, you may say to yourself, Jay, how does any of these pictures relate to the field of differential equations? Well, every one of these pictures can actually be described in some way using a differential equation. For example, this first one here, we have a cancer cell, and modeling cancer growth or the spread of diseases can be used using the language of differential equations. Same goes for here. We have a simple electrical circuit, and the movement of electricity and how does electricity described in different situations can be also described using differential equations. We have a chemical reaction, and many chemical reactions are modeled using differential equations. So we have a example here, the simple pendulum, which is actually something I plan to go over in this series, and how to model it using differential equations. We can model these quite well, and in other physics, we have waves and chaotic systems. Those take advantage of differentials, as well as the stock market. Many big time firms hire people with PhDs in mathematics, because differential equations can actually describe and model different market trends and how the market can change over time. And so you can see how differential equations is actually quite important to our day-to-day lives. And now that we know how differential equations are useful, what is a differential equation? We take the second part of differential equations. It's an equation. It's an equation, and based off of the first part of differential equations, we can understand that it has something to do with derivatives. So a more formal definition would be it's a equation that contains a function and its derivatives. So let me give you an example. For example, we may have the derivative of y with respect to x plus 2 times y is equal to x plus 3. I just made this up. Here we have the derivative of some function plus 2 times that same function is equal to x plus 3. This right here would be an example of a differential equation, and we can actually have different notations to describe a differential equation. So for example, another notation you may see is y prime plus 2y is equal to x plus 3, and another notation you may see is the derivative of some function of x plus 2 times that same function is equal to x plus 3. Here we have another notational representation of this same first equation I showed you, and for the remainder of this series, I am mostly going to focus on this notation, along with some expressional examples of this other notation right here. But it's important to know and familiarize yourself with all different notations. Now that we know what a differential equation is, what is the solution to a differential equation look like? Because a typical equation, let's say we have x plus 2 is equal to 3, right? We have a more discrete constant solution. So we have x is equal to 1, for example, would be the solution to this equation right here. 1 plus 2 is equal to 3. But for a differential equation, we actually have a set of functions that represent the solution to our differential equation. Now, what do I mean by this? So let's take the differential equation, for example, y double prime plus, when I say double prime, I do mean the second derivative of y with respect to x, plus the first derivative of y with respect to x, 2 times the first derivative of y with respect to x, minus 3 times that same function is equal to 0. Now, I have the solution to this equation. The solution to this is y, our function y of x, is equal to e to the negative 3x. Now let's go ahead and see this, like let's not take my word for it, and let's actually evaluate it ourselves. So if we take the first derivative here of this function, we end up with negative 3e to negative 3x. And if this is unfamiliar to you, I encourage you to review your derivatives, as they will be very important for this entire series. So it's important not to get left behind. For our second derivative of our function, we have 9e to the minus 3x. So let's go ahead and let's plug that in, and let's see if we do indeed get 0. So if we get 9e to the minus 3x plus 2 times negative 3e to the negative 3x, we have minus 3 times our function of x, which is e to the minus 3x. So if we evaluate this here, we have a e to the minus 3x here, e to the minus 3x here, e to the minus 3x here. So the only difference in all these is their constants. So if we pull out an e to the minus 3x, let's go ahead and pull that out, e to the minus 3x, out of all of these, because they do share that same like term. What we'll end up getting is 9 minus 6 minus 3. And if you evaluate this, some simple math wizardry here, we have 9 minus 6, that's 3. 3 minus 3 would be 0. So we get 0. We get 0 is equal to 0. So this indeed is a solution to our differential equation right here. And what you'll end up finding later on is that you can actually have a set of solutions that represent different types of solutions for our differential equations. So what does that mean? So for example, another solution we may have, so y sub 2 of x is equal to e to the x. So let's go ahead and let's try to solve this one as well. So we have y, and then we have the first derivative. We have the first derivative of our function, which is also e to the x, and derivative of e to the x is e to the x, and second derivative of e to the x is just e to the x again, right? And so if we go ahead and we plug those all in, what we'll end up getting is e to the x plus 2e to the x minus 3e to the x is equal to 0. So we have a 1 plus 2 minus 3, so that's 1 plus 2 is 3 minus 3, that's at 0 again, so we get 0 is equal to 0. So we can see that this over here also represents a potential solution that we could have come up with for our differential equations. And you'll see this theme reoccurring and again, is that differential equations can have more than one type of function as its solution. And what I hope to accomplish in the next video is to go over the different types of differential equations and different characteristics that they may have, and also talk about some more formal definitions for differential equations that you may need to familiarize yourself. And with that, we will have the proper foundation to go ahead and solve our first differential equation.